Okay, so the next thing, now that we have the expression for the variance, and so in principle we know how to calculate it because we know how to calculate functions of expectations of functions, and x minus mu squared is just a function of a random variable, so we could calculate that. But there are easier ways to do it. By the way, I mentioned that up here, I should have said that we did make this assumption that expectation of x squared was finite. And the reason we had to do that was that if it's not finite, then this value, this mean squared error, is just infinite all the time. And so there's really nothing we can do to minimize that. Okay. So this is the computing formula for variance. And here's how it works. So we have a random variable x has a mean mu. And standard deviation. Sigma. Okay. Remember up here, we decomposed the expectation of x squared. Sorry. We decomposed, my apologies. There was a typo here. There should have been C. We have this decomposition. So if we set C equal to 0 in the above statement, what do we get? We get expectation. Well, first, let me just copy down what we're dealing with. We set C equal to 0, so C is going to disappear. C is not in that term. C is going to disappear from here. What this tells us is that expectation of x squared is equal to expectation of x minus mu squared, the variance, plus the mean squared. I want to comment here, just to be clear, moving forward, a lot of times parentheses and brackets and so on will get in the way when there's just going to be too many of them as we progress through. So with expectations, it's not really necessary to write the parentheses. With the expectation E is what's called an operator. It operates on a variable. And so I will often omit the parentheses as long as it's not going to create confusion. So just be aware of that. So what this then gives us is, let me take this expectation and let me write it. This is the square of the quantity. Okay, something to be aware of here though is this is the expectation of x squared. This is the square of the expectation. They are not the same. And if we rearrange this, the computing formula for variance says that the variance, so this is obviously the variance here, that the variance of x can be computed as the second moment, or the expectation of x squared, minus the square of the expectation. So that is oftentimes the best way to calculate variance. Because, well, it's just easier, right? To calculate the variance, you need to have the expectation anyway. So the second term, the square of the expectation is easy. And then to calculate then really what we need is the expectation of x squared, which is easier in general than having to worry about subtracting off the mean, squaring that, and taking the expectation using the law of unconscious statistician that we talked about before. So let me just show how an example of this would work out for a Bernoulli trial. So the variance of a Bernoulli trial. So remember what a Bernoulli trial is. Bernoulli trial is a random variable x is Bernoulli P if what that means is it has a probability mass function which assigns value P to the value 1, and otherwise it assigns value 1 minus P to 0. Sometimes we write this as Q, but we don't have to. Okay. Then what's the variance of x? Well, to calculate the variance of x using this formula up here, what we have to do is you have to be able to calculate the expectation of x and the expectation of x squared. So what's the expectation of x? So in general, the expectation of x, the sum over all values of x, of the weighted average, it's the weighted average of all possible values where we weight by the probability masses. Well, in this case, there's only two possible values. There's 1 with probability P, and there's 0 with probability 1 minus P. So the expectation of a Bernoulli P is just P. What's the expectation of x squared? Well, by what we call the law of unconscious statistician, we can just plug in. This is why this is such a good, so powerful. We can just plug in that function x squared, but we get to keep the same probabilities, right? We don't need to recompute the mass function of this new random variable x squared. Okay, so this is 1 squared times P plus 0 squared times 1 minus P. So the expectation of x squared is also just P. Makes sense because incidentally, the two possible values of the Bernoulli, 1 and 0, if you square them, they don't change, right? So there's no real change in squaring this random variable. But from the computing formula, what do we see? Variance of x equals expectation of x squared minus the quantity expectation of x quantity squared. So this is P minus P squared, P times 1 minus P. And the standard deviation is the square root of that. So that's how we use the formula. Something to be aware of, something that is somewhat that actually comes up reasonably often in some applications, and it's worth being aware of, is Bernoulli random variable. Take the possible parameters in a Bernoulli random variable are between 0 and 1. And what's interesting is that the variance, so it's a quadratic, right? It's quadratic in P. This isn't the best quadratic, but we do our best here. Oof, man. See if I can figure this out. All right, well, that's about as good as it's going to get. The variance and standard deviation of Bernoulli is maximized at the value of 1/2. Okay, so the hardest Bernoulli trial to predict, or the hardest outcome to predict, is a fair coin toss, right? Which makes sense, because it's 50-50 either way. What are you going to guess? Whereas if we had a 90% probability of heads, a 10% value of tails, we know that we just predict heads every time. Yeah, we're going to be wrong whenever it's tails, but that's only going to happen 10% of the time. The variance, the expected error is lower in that case. Okay. So that's how we compute variance. That's how we calculate it, specifically in the case of the Bernoulli trial. In the next chapter of these lectures, we're going to go through a bunch of discrete probability distributions, and we're going to calculate mean, variance, and various properties of those specific well-known distributions. The Bernoulli is one of them, but Bernoulli is so easy. It's such a simple distribution that we could just do that here in this example.